All right. I see it on the stream. I think we're good. All right. I guess here we go. On the stream, I think we're. Welcome everybody to. I think it's the first virtual Starry Nights of the year. Welcome to 2021. We have a wonderful show for you guys tonight. With us, joining us, is our moderators today, Indira, Abby, and from the Royal Astronomical Society of Canada, we have Haley and Karambir. Welcome, everyone. And also my co-host for today is Matthew Simone.
Hello.
So we are ready to get started. So now the thing that we got going on today, now while the moon is quite a spectacular thing to see, it is also a very sinister thing to see in from an astronomer's perspective, because with all of that light and glare, we can't really see a lot of wonderful things.
It's a very jealous celestial object. It wants all the attention. It's like, look at me, I'm bright.
Exactly. Oh my god, it's it's fun and sometimes not fun. But so while the nebulous objects, we won't be able to see a lot of those, but we do have a lot of star clusters and star stuff going on today. So I think this is going to be a rare and good time. So I think without further ado, we can go to our first object, which is going to be the Orion Nebula. Here, let's try this out here. Oops. Okay. If I can spell it right. Oh my god.
This is why the find function is good enough, where it's like, I think I know what you're talking about. A lot of the star names and spellings are very obscure. So you're like, I don't remember how this is spelled, because it's like, or it's in 5 different catalogs. So it's like in one of them, it's like NGC5, but in another one, it's like Messier 74 or whatever. And you're like, oh, what's going on?
Yeah, there's like 20 different names for it. Okay, maybe, hold on. Can you take over the live stacking really quick?
Yeah.
Because I just want to see it once.
Okay, so.
Gotta keep going, yeah.
Get going. Okay, so have we slewed? Did we move
forward?
We
I think we're there.
Okay. All right. So our telescope has, let's turn on the stack. So for those of us who, if you've been here before, but just to kind of like talk about how this works, how stacking works is that we're taking photons of light and putting them all together into one giant picture. And so it's like you can think of it as like a photography sandwich. So we're going to start off. The first image is fainter, and then it gets brighter from there.
Ooh. Yeah, just looking at the chat. Hello, and also Jennifer Kirky will be joining us as a moderator as well. She's from Douglas College, and she teaches physics and astronomy. Another welcome addition to the team. All right. So yeah, so just while we're kind of getting things going for the Orion Nebula, just to talk about it for a bit. So with the now I did say at the beginning in the introduction that a lot of the nebulous objects in the sky we won't be able to see too well because of the full moon. The Orion Nebula is the exception, because it is so dang bright. And it's really one of the easiest nebula that you can actually find. As long as you can identify the Orion Nebula or Orion constellation, and usually it's popular due to the 3-star belt, you can actually find it. It's just a little fuzzy patch just below the belt, and that's actually the nebula, which is incredible. And within the nebula, because it's so bright, it's actually the brightness is actually due to 4 super bright, super big stars called the trapezium, I believe. So it's 4 stars right in the center of the nebula, and with all of that radiation and energy being emitted from the stars, it reflects and excites the gas in the nebula, and that's how we can see it. So it's really quite extraordinary.
And
Um,
unfortunately, at the moment, it is not showing up. So I'm
oh,
wondering if we might be a little bit off on our targeting. So I just reloaded the pointing model to see if maybe that will put us back on target. So I'm going to point off and
sure.
then point back and then see what
Okay,
happens.
cool, cool. Then I'll keep talking.
Yeah.
Okay, so yeah, so within the nebula, we have about 700 stars that are forming. And the thing about the Orion Nebula is actually an example of something called a stellar nebula, which is the starting point of all the stars in the universe, essentially. It is these nebulae are primarily made of hydrogen and helium, which is the building blocks for stars, what it needs to fuel, or what it needs to for to start nuclear fusion. But that's where stars are the starting point of all stars. Eventually, once stars grow up and die, if the star was big enough to begin with, it'll actually explode or give off its outer layers to either become a planetary nebula or a supernova remnant. But we'll talk about that a little bit later. But just to know, the stellar nebula is the starting point. Um, what else we got? Yeah. So basically, with all of these stars that are forming in the nebula, it sums to around a total of 2,000 solar masses worth of stellar formation in that nebula. So it's quite incredible star factory, and it's again because it's so bright. It's partly due to the trapezium, but also due to its proximity to Earth. It's actually one of the closest star forming regions to Earth. I think where is it? Oh my god! I actually forgot how far away it is. Oh my god! Come on.
In the meantime, we've got the trapezium to
Jump
show
on
up a
this here.
little bit, but that's about it. And I'm trying to figure out if I'm going to dump some of the calibration files and if that helps.
Oh,
No, I don't know. Huh.
we're getting close there, but as you guys can see, like those little four bright stars in the center there, um, are is the trapezium, the four bright stars that give the glow of the nebula. Um, yeah, okay. So the distance, it's one of the closest at about 1,300 light years away. So it's still an unimaginably far away, but close enough that we can see it. And these stellar nebulae, because they're a vast collection of stars, they're actually quite large as well. The Orion Nebula is actually about 24 light years across from end to end. So it's really quite incredible. What are they? Nebula, yeah. But maybe just a little more about the trapezium. Um, the actual four stars that you see there are actually about 1.5 light years in diameter from one star to the other, about. Um, and in the center, like maybe what actually brought them together in the first place, is there could be a black hole in the inside, maybe. Um, or maybe it's just the gravity of the surrounding stars that brought them together. Uh, I think what do we got going here? Just
Yeah, having a
looking
hard
at the
time.
screen.
Yeah, getting anything to come up. So I've just switched.
Oh,
I switched our imaging mode to see because yesterday this turned out really bright, and I'm hoping that the increase in moonlight between yesterday and today wasn't enough to like outshine the entire nebula because that
oh.
seems like yesterday we tested this yesterday and it worked out fine.
Mm-hmm.
So now Orion Nebula is embarrassing me here a little bit by not showing up
Oh.
for me.
Off to a great start,
Yeah, no,
as always. All right, let's have a look at the chat really quick. Nothing too much going on. Everyone's having a good time. Awesome, awesome, awesome. What else can we kind of talk about here? Actually, I'll talk about this as well. Within the Orion constellation, actually in the belt itself, There's two more uh, prominent. Well, actually, they're not very bright, but they're very recognizable nebula. One of them being the Horsehead Nebula, which is just it looks just how it sounds. It's just this dark horse head, just kind of looking up in the blackness with a background of what looks like a sunset of colors, actually, which is kind of neat. But right next to the horse head, we also see, or there is also a nebula called the Flame Nebula as well, which looks just how it sounds. It's just a big, it looks like a lit fire, which is incredible. But yeah, because we were testing this yesterday and with the moon, we actually weren't able to see the Orion Nebula, or excuse me, the Horsehead or the Flame Nebula, which kind of sucks. How are we doing there?
Yeah, it's not amazing. So, anyways, I just restarted the camera software just to make sure it's not a glitch. It's possible that where the moon position is today relative to yesterday, when we were trying some of the targets, has changed so much that it's actually washing out the entire nebula. Um,
Holy shoot! Okay.
so, because we were chatting about the trapezium cluster, so here's trapezium here in the center,
Mm-hmm.
and so this bright patch of stars. But yesterday, this nebula showed up really well, and so I'm surprised that it's not pulling in it all today. But let's
Oh
I
dang!
just refreshed it and see what happens. That was supposed to be our big grand opener.
Yeah, not a good sign, but I think we can recover. If maybe we'll give it a couple more attempts here, and we'll see what happens. But maybe while that's going on, I'll also talk about the life cycle of a star. Why not? So again, like I said, the Orion Nebula is a stellar nebula, which is essentially the starting point of a star's life. Forms something called a protostar, and what that means is it's just a concentrated ball of gas and dust that's slowly heating up due to friction from all of the particles rubbing up against each other. Eventually, the star will hit a critical temperature that will actually ignite nuclear fusion. Can you hear me?
You're still there.
Oh, okay. I didn't drop off. Okay. Um, yeah, that's one thing is kind of the internet's a little spotty right now. So I will forewarn that I'll probably cut off every now and again. So that's why I'll try my best. But anyway, yeah. So what'll happen is it'll form a protostar, um, which is like I said, is just a concentrated ball of gas and dust, and it'll hit a critical temperature. Whoa, there you go. Close up view of trapezium. Um, then the protostar will hit a critical temperature where it will begin to fuse hydrogen into helium. And this is when a star is defined as a star, when it fuses hydrogen. And then what will happen, since once this ignition starts, it'll actually, with all of that burst of interstellar radiation, it will push away the surrounding gas, and it's now a star. And sometimes there are nebula that actually have hints of this, where I think it's the Bubble Nebula that's an example of this, where once a star is ignited, it'll release this, the radiation from the fusion will push away the surrounding gas, but over time, that surrounding gas will expand and create a bubble. And people in the in the chat, if you know more than me about this, correct me, because I believe the Bubble Nebula is an example of this, which is really really cool. Um,
So unfortunately, I don't think we're going to be able to pull up our nebula. I think we're
uh-oh.
just getting too much of um,
The moon.
maybe of the moonlight that's coming through. So I think that's kind of what's going on.
All
But
right.
unfortunately, so maybe we could come back to it. It might be just the angle that moonlight is falling into the dome right now as well. So it could be possible that if we check Orion back later on in the evening, it might be possible to find it later.
Okay.
Thanks for carrying that one, though.
Yeah.
Right?
Yeah, of course.
While we
It's
can't
like,
see anything, let me tell you all about stellar formation. Good job, Kyle. That was amazing.
I'll tell you a story. Well, it's kind of like radio where it's like dead air or
I
some
know.
shit.
Yeah.
Anyway,
It's fantastic. High quality
you're
content here from the Trottier Observatory, everybody.
channel
So
95.6.
who needs a
Trust
telescope when there's just, we could just tell you a story about stars.
Totally.
Yeah. That's neat though, because when you're talking about like that moment where like, our sun would have had that moment as well, where like, nuclear fusion began. And that's the point between being like just a ball of gas and an actual star. Like the star comes to life like that, whoosh,
Oh,
and that happened to us like 4.5 billion years ago, right? That's part of our story,
yeah.
which is really cool.
So incredible. I guess, okay, now that we talked about the sun, I will just go on this little bit of tangent before I guess we move on to our next target. So, star will go through his life, and then, depending on how big it is, it'll actually explode as a supernova, and will release all of the elements that were fused in its core, like oxygen, nitrogen, calcium, and iron. And if these elements sound familiar, they exist in our blood and in our bones and in the Earth's crust, which is incredible because what that implies is that maybe our solar system formed inside a supernova remnant or the corpse of a long dead star. And that's one of the leading theories of how our solar system was made, because how are all these elements formed? Well, in the cores of stars. But I thought I'd share that. Now, because of the moon, we can't actually look at these stellar nurseries, but maybe next time we can, when the moon is not so intrusive. But yeah, there's a little astronomy tip of the day, which is really, really cool.
Yeah, I think that also provides some like, I don't know, it makes me feel more connected to the universe and to
Yeah.
one another. Think about that. It's possible, Kyle, that you and I are atoms. We're all boiling together in the same core of a star at some point.
Oh my God, boggles the mind.
It would boggle the mind.
Um,
Okay, so we switched targets.
okay, what do we got? Yeah.
So I moved us over to this is a cluster. It's a double cluster in the constellation of Perseus called NGC 869. One of the reasons why this might show up a little bit more. Okay, yeah, it popped up right away. The telescope's almost looking completely straight up right now, so we're also looking through a lot less atmosphere. And so when we are looking at a target, actually, a friend of mine messaged yesterday and said, like, I see this glowing, flashing blue and red object on the horizon. Like, what is that? And I'm like, that's the star Deneb. And so they're like, why is it flashing red and blue like that? And it's from the light of the star passing through our atmosphere. And the light gets mushed around by the air and split apart. It's called refraction, and so we can see it in different colors, a little bit of blue, a little bit of red, and it has that twinkling effect. When you're looking along the horizon, you're looking through a lot more air before you get to space than if you're looking straight up. If you're looking straight up, you get 100 kilometers of air if you're at sea level, which we basically are. But if you're looking along the horizon, you could be looking through hundreds, thousands of kilometers of air, so it ends up being a lot more soupy down on the horizon. So this is almost straight up. So we're looking through less air, and hopefully there's less glow up here. So this is actually part of two clusters. Now, the observatory field of view is such that we can only see one of the clusters at a time. So I'm going to show you one, and then we'll go through to the other. And because this is part of Perseus, this constellation or this cluster of stars is supposed to be the scimitar that Perseus used to cut the head off Medusa, if you're looking back to mythology. And so it was first found by Hipparchus, which was an ancient astronomer back in 130 BC. Look at that. People have been looking up at the sky for centuries and centuries and centuries. And so there's 300 white blue stars and 175 in one of the clusters. The other cluster is called NGC 884, which we'll be looking at in a second. And there's 175 in the other clusters, about 700 light years away. Now, cool thing about this, this is we're talking a little bit about geography of the solar system, or of the galaxy. What do you call that? Galaxography? Instead of geography? I don't know what would the name of that be. Anyways,
I like it. I like
galactic
that name.
structure. Yeah. So just kind of, I'll pull up some of the spiral arms of our Milky Way galaxy here for 1 second. So I'll grab a map. Dun, dun, dun. So here's our Milky Way. So we basically look like this. Let's bring this picture up here. Dun, dun, dun. Stretch this so you can see it properly. Another thing to notice, if you ever see us like struggling trying to do things on the computer, it's because we're at home ourselves. And sometimes things like when we drag the edge of a window, like our mouse from the computer, there's a delay and it doesn't tell us if we're on a thing yet. So it's all hands off these days while we're doing the stream. Okay, so here's an image of the Milky Way galaxy, and there's different arms of the galaxy. So we live here. This is where our sun is. It's part of something called the Orion spur, and there's an arm here that's called Perseus, and the name of this arm is actually named after an association of large stars. They're called OB stars. So there's several different classifications for stars. The biggest ones are class O and B. They tend to be bright, large, blue, supergiant stars. Color kind of works opposite in space the way that we think of it on Earth. So the cooler things are red, hotter things are blue. So the hottest of stars are blue, the coolest are red, and we're kind of in the middle, yellow, white star. Our own. So when we're looking out toward Perseus, this arm, so we're here, so imagine looking out toward this spiral arm of the galaxy, which is a few thousand light years away, you would notice this cluster of stars that are in that direction. And some stars that are more loosely associated with one another, so they're not as tightly gravitationally connected to one another, are called themselves associations. So they're, rather than a cluster of stars, they're a stellar association. And so there is an association of these massive stars that are in this direction, and that name of stars lends its name to that entire arm of the galaxy. So when we look in this direction, we're actually looking past our little spur of where the sun is, past this void of stars in this part of the galaxy, toward another arm. So it's kind of neat. When you're looking at this cluster of stars, you're looking toward in the direction of another arm of the entire galaxy, which is this cluster lends its name to it, which is pretty neat.
Oh, so cool? Awesome.
I know.
If I could actually interject with another neat tidbit, totally unrelated to the cluster that we're looking at. But if I'm good, okay, hold on. Can I just grab the mouse really quick?
Please. Yeah,
so I'll kind of do this. Okay, so one little thing about the galaxy. It takes, like, everything rotates in space, essentially. It takes 1 year for the Earth to rotate around the sun. Likewise, it takes the sun about 230 million years to orbit the galaxy once. And an interesting little tidbit is the last time the sun was in this relative position in the rotation of the galaxy was when the dinosaurs were first climbing onto land, or were first evolving. Like 230 million years ago, whatever was happening then, that was what was happening then. So it took 230 million years for the sun to orbit the galaxy once. And that was what was happening the last time the sun was in this position.
So technically then, dinosaurs lived on the other side of the galaxy.
Yeah.
Right?
Like yeah. Like it was, oh my God, it's nuts. It's awesome. But no, that was just a little interjection there. I thought that was really cool. Well, we had the picture of the galaxy up. So, yeah.
Thank you. All right. So yeah, this is one of the clusters, and they're young. So clusters of stars like this, and this is kind of one of the themes of today, because we had to focus on objects that we could see in this bright moonlight. So we had to pick really bright objects. So we had to go with bright star clusters. And so these bright clusters of stars tend to be newly formed. And so they're not very old. This one is anywhere between, the estimates are like 5 to 13 million years old, which sounds really old, but remember, stars can live for billions and billions of years. So our sun itself is 4.5 billion years old, and so these are actually pretty young clusters of stars. Now, one of the largest, and it's just sort of off the picture, so it's a little bit more in this direction. We actually might be able to see it in the next field of view. The largest star that's part of this group is called 9 Persei, and it is a blue supergiant that's 10.5 times the mass of the sun and 12,000 times brighter than our star. Which is pretty amazing. I heard once an estimate that if you were standing on a planet that was around a blue supergiant like that, you could face the opposite. So the star could be behind you. You'd be standing on the planet. The star could be behind you. You could have your eyes closed, and it would shine. The light would be so bright that you could see the bones in your hands. Like the light would shine right through your body.
Oh my God.
You wouldn't live very long, obviously, but yeah. Okay. So this is part of a double cluster, and I'll show you now. This is also a chance to, and as we're steering the telescope, kind of show you the field of view that the telescope has. So I'm going to zoom in here Um, on SkyX, which is the software that we use to steer the telescope, it literally just has the sky, and we point at it, and it makes the telescope go. It's actually pretty handy. It also spoils me because we have people, part of the Royal Astronomical Society, that like have memorized the sky properly, like you're supposed to, and they use manual telescopes and will point them by memory as to where you need to go, and it's pretty awesome. I think Carl Miller is in the chat right now, and he was one of those people that has like a old school like wooden tripod with no computer, and is like, hey, I'm just gonna point it, and here it is, like done. So
it's an incredible telescope.
Yeah.
That it's awesome.
So this square here is the field of view of what our telescope sees. So when you're looking at the camera, this is an estimate around. So if you're pointed at a target, like where this red thing is here, the computer's showing you kind of where you're pointing. So this is part of a double cluster. So now I'm going to go head over to this part of the cluster. So we're going to move the telescope over, and we'll check out the next side of it. And
yeah, while this is actually happening, I'm not sure if you've mentioned this actually, Matt, but this is the double cluster. But the thing is, this is one of my favorite objects for this reason, actually, is one of the clusters in this object. So I'm actually forgetting which one, but they're not actually side by side. One of them is actually about 1,000 light years farther away.
yes, yeah.
But because of our position, like of our vantage point, they look like they're right next to each other.
Mm-hmm.
And that's just kind of a good example of that, it looks like space is 2D from where we are, but you have to remember this is a 3-dimensional space that we're occupying. It's awesome.
Oh, I get some motion in that one, so I'll clear it out. Yeah, it's cool because I've seen in even the planetarium shows that sometimes we'll do at H.R. McMillan Space Center. We had when we were doing that before we got all locked down and we weren't allowed to open anymore. But for the theater shows, anyways, the actual planetarium shows. But you could trace out the constellation lines in a constellation and then move through 3D space and see how the lines get all stretched out. Because from other vantage point, the constellations don't make any sense anymore, right? Yeah. So anyways, here's the other side of the cluster. It kind of looks very similar to the other one, but again, as Kyle was saying, they're not actually beside one another. They're kind of part of a stream of stars that are moving in that arm of the galaxy, but are ultimately one's farther than the other one. Cool.
Ooh, cool. Love it. Love this. Okay. Yeah, and I think kind of one good indication to tell of a star cluster's age is their proximity to one another. So if they're really tightly packed, that means that they're an older constellation because there's been enough time for those stars to gravitate towards each other. And open clusters are usually younger because they haven't had a lot of time to gravitate towards each other. But also, with another indication, is that the color of the stars are indicative of how old the cluster is. So if there's a lot of blue and white stars, that probably means it's a younger cluster because blue stars are hotter, they're brighter, and they burn through their fuel much quicker than red stars, which are typically cool. They're cooler, and that means they're slow burning through their fuel, which is kind of good indication of the age of these things, which is cool. Yeah.
That can also, I was just jumping off of that too, Kyle. That also tracks on the ages of galaxies too. So we can see an entire galaxy shift redder in color as they age, which is pretty cool. So you can tell this is actually Dr. Joanna Wu's specialty is in galaxies and galaxy formation. But we can actually see whole galaxies turn redder in color as the entire star population of that galaxy ages, which is pretty cool.
Yeah. Awesome.
Want to move on?
Yeah. Let's look at some other cool stuff. So what do we got going on? So what's next? The beehive cluster. Yes. Awesome. Okay. Oh, okay. Let's give this a try here. So go like this. And we go. Oh, yeah, we're zoomed in. Remember? So oh, do
Also gives you an idea of just
zoom
how
out.
many stars are in the sky.
Yeah, really. Yeah, this program went through a recent update, and they just packed this program with stars. So that's great. Bada boom. That go boink. And then oh, oops. Oh, okay. Again, learning the ropes. Then we could do this. All right.
Oh, Cooper
Oh,
asked a good question here. He said, how do we know how far away stars are? And that's a great question, Kyle. How
oh,
do we know that? How do we know how far
that's
away
an
things are?
excellent question. There are different methods to find the distances to things, and actually a very good one, but it only works for very nearby objects. Actually, here, if you want, do you want to take over the
Yeah,
the
yeah,
sharp cap while I kind of do this?
sure.
Yeah, yeah. So there's a lot of ways. One of them is talks about the parallax of something. So, and you can actually do this yourself right now. If you, and I'm doing this actually as I'm talking, if you hold out your thumb at arm's length and close one eye, and then you're also looking at the background of your thumb, which should be a little bit farther away. But anyway, close one eye and then open it and close the other eye. And if you do this repeatedly, you see that your thumb kind of, it looks like it's moving back and forth, right? This phenomenon is called parallax, and we use the same technique to figure out the distance to nearby stars.
Hey,
So
Kyle,
and
can I
how
just
we
pause you for one
oh yeah,
second? You want to
yeah,
know a
yeah,
funny
what's up?
thing? I know why
Oh,
we weren't able to see other stuff.
oh no,
The
what did we do?
observatory dome is not entirely open.
Oh my god.
So I was like,
Oh,
why is it? Because I just tried to look at something else that I was like, Beehive, we should be able to see it. I couldn't see it. And I was like, it's about the same altitude as the Orion Nebula. So the dropout shutter on the dome is not
oh,
open. So that is why.
oh.
So I will fully open the dome and then we'll be able to see outside into space. We're experts, everyone. We're
Oh my
experts.
god, yeah. Astronomers are humans too. Don't
Yeah.
worry. We're fun. Okay. Um yeah, so now that we actually open the bottom shutter, we can actually see more stuff. But yeah, okay, so just kind of keep going here. So parallax, looking for nearby stars. So what happens is when the Earth is on one side of the solar system, we take a picture and say we want to know the distance to a particular star in that field, and then we want to know the distance to a particular star in that field. We take a picture on one side of the solar system. What that's supposed to simulate is one eye is closed. Then we wait for half a year, 6 months, until the sun or Earth is on the other side of the solar system and snap another picture. And then what we do is we compare the two photos and we can see if the star has jumped, essentially, compared to background stars. And then by using fancy geometry and math, we can actually figure out how far away that star is. Now, this is also, while this is a great technique, it only works for nearby stars. This does not work for telling how far away a galaxy is compared to other galaxies. It's kind of like saying if you're driving down the highway at a particular speed, the trees that are right next to you are whizzing by your face, right? You know how far away that tree is compared to, let's say, the mountains that are in the background. They're moving very, very slowly. And that's why we can use parallax for taking distance measurements of nearby objects. But if you want to know how far away the mountain is in the background compared to a farther away mountain, that's going to be very, very hard. So that's why parallax doesn't work for, let's say, galaxies, telling distance to galaxies, or even just far away stars in our own galaxy. Like the parallax method only works to probably, oh geez, probably about 50 light years or 100 or something. probably more than that. Jennifer would know, or other people in the chat would know. Um, but yeah, that's only one of the methods of how we measure distances to particular things. So that was a very long-winded answer to that question, but it's a really cool thing to do, and you can actually do it. You can observe this parallax phenomenon with just your thumbs or trees and mountains and cityscapes, which is kind of cool. Okay, awesome. There you go.
It's great. Yeah.
Yeah.
Yeah, and then like some other objects, we know we can compare brightness between some things. So we know that, like for one thing, an example. There are some variable stars in the universe that we know generally how bright they're supposed to be. So if we compare two of those stars, one in the distant universe and one that's closer to us, and one appears fainter than the other one, we know that faintness is a function of its distance away from us. We call those standard candles, which is pretty cool. And then for galaxies, distant galaxies, they are shifted. Their light is stretched as it comes across the universe, and we can measure the amount of stretch by the time it reaches us, and then we know kind of generally how far away that galaxy is. Beehive cluster is pretty diffuse, and so we got some of the stars here. But Kyle, if you want to talk about it, I'll see if I can get us like some more dense parts of the cluster.
Definitely. All right. So the beehive cluster is kind of one of those hidden gems. There's the Cancer constellation. Oh, this is where the object is actually located. Is in the constellation of Cancer, and it's kind of a dim constellation, like very dim, very hard to kind of see. But if you can find it on a very dark and very dark night, you can find it with your telescope, and it's actually a decently bright cluster. But anyway, in the Cancer constellation, it's about 630 million years old. Now, like we said about the lifespan of these objects, 630 million years old is actually very young in astronomy terms. In this cluster, there's a lot of blue and white stars, and it's very diffuse, so it's very, very young. And it's about 580 light years away, so pretty much in our own backyard in astronomical terms as well. And yeah, it's not dense with stars. They're just beginning to attract each other to a central point. And actually, I didn't know this until I was doing some research on this object, but it was actually one of the first objects that Galileo observed with his telescope. And I think that's mind-boggling. Like when he was looking at Jupiter's moons to develop his heliocentric model, he was also looking at this cluster, which is pretty cool. It has a total mass of about 600 suns, so quite a lot less than the double cluster, I think. What else got? And yeah, like I said, it's pretty bright. It has a magnitude of about 3.5. And now that I mentioned magnitude,
What's magnitude, Kyle?
oh, I'm glad you asked, Matthew. I'm gonna tell you. Magnitude. It is the measure of how bright particular stars or objects or galaxies are in the night sky from where we are. There's two different types. There's absolute magnitude and apparent magnitude. I won't go into too much detail here. I'm sure people in the chat will just jump on this as well. But I will talk about apparent magnitude just for the purposes of this. So it sounds just like it is. It's how bright the object looks like from Earth. It's how apparent the brightness is. But anyway, what it means is the higher the number, the dimmer the object is. And magnitude goes into the negatives, actually. With magnitude 0 is, or the object with magnitude 0, which is supposed to be our standard for this scale, is the star Vega. And for any movie buffs out there, the movie Contact, which is one of my favorites, which is based off the book by Carl Sagan. Spoilers from a '80s movie. Vega is where the extraterrestrials first sent out the signal, or rather the response
I thought you
to
were going to say
our
spoilers.
signals.
They actually make contact. I was like,
Yeah,
what? Really?
that's pretty obvious. Yeah, they
No
make
way.
contact. um, but yeah, that was from Vega, so that's kind of a cute little tidbit there. But anyway, magnitude. So this goes into the negatives. Numbers can go into the negatives, and as an example, I will say that the full moon is a magnitude of about negative 13, and the sun, it has a magnitude of negative 26. Now, the difference between, let's say, magnitude 0 and a magnitude of 1, what that means is a magnitude 0 thing, or the difference of 1 unit of magnitude, is 2.5. So what that means is a magnitude 1 thing is 2.5 times dimmer than the magnitude 0 thing. And just to also give you another example, so I'll go back to the moon and the sun. So the moon was a magnitude of negative 13, and the sun is a magnitude of negative 26. So if you do the multiplication, the sun is about 150,000 times brighter than the moon, so which is pretty staggering, I have to say. But yeah, that's essentially how magnitude works, and it is what we use to measure brightness in the sky. But thank you for asking that question, Matthew.
Oh yeah, no problem. Uh, no, it's actually one of those things where I was like, and we have a threshold cutoff for generally what we think our camera will be able to pick up on a given night, and we had to adjust that for this evening because of the moon's brightness. So we're trying to find a cutoff of what objects at what magnitude, we got to find. So thank you for explaining what that actually means, because as we're going, as we're trying to find targets, it's good to know. And you're going to hear that. You're going to hear people talking about the magnitude of objects when you're looking for them, and you'll see that listed as a function. I've moved us to another cluster here, Kyle, and then I thought after this is the starfish cluster. And when we're done this, why don't we go back to Orion to see if we can actually see it, since we opened the dome properly this time.
I am so down.
Okay. Hooray. Okay, so this is the starfish cluster, and so called because, and you can kind of make it out here, but you can see these kind of like arms going up in this direction and then sort of loosely in that direction. But when people look at it, or when in the sky, it basically makes the shape of a starfish. And it's an interesting target because it's sort of oddly shaped. We know that clusters of stars can actually basically do one of two things. They can either clump together if they've got enough collective mass. They will collect together. The largest clusters of stars that we see in our galaxy are old clusters. They're called globular clusters. So the very opposite of most of what we're seeing tonight, which are young clusters of stars. Globular clusters are very old, and they can have tens of thousands or even hundreds of thousands of stars, whereas open clusters tend to have maybe a few hundred to a few thousand. There are less of them. But this one's kind of all stretched out, and one of the reasons why it's got these arms that kind of go all which way in whatever directions, if we think that there might be the activity of gravity pulling on it from another nearby cluster, has stretched it all out in different directions. So this one's about 3,500 light years away. It is 290 million years old. So again, it's old. It's older than some of the other clusters that we've seen that are only 5 to maybe 10 million years old. But it is still much younger than these old ancient clusters of stars that we see in parts of our Milky Way that it can be billions and billions of years old, like left over from the galaxy's early formation. And we're going to talk a little bit about that later, about why galaxies will form these older clusters of stars. And but yeah, so this is in the constellation of Auriga, and it's all stretched out like this. Its arms splayed in various directions because of this gravitational interaction with these neighboring clusters. And so, like as Kyle was saying earlier, our galaxy is spinning around. We look at it as a static thing, and certainly on our time scales of human existence, they seem static. But the stars are mixing and swirling around with one another, and we see micro chapters of that story by looking at the objects in the sky and how they're shaped and in what direction that they're moving. And so, but if we were
Oh,
to fast forward this over time, all these our night sky would look totally different. Millions of years ago, all the creatures of the earth over eons of time have looked up at different skies than we see now.
oh my God. Can I do a plug of something really quick,
Please, yeah.
actually? So one of my favorite videos on YouTube is by a guy called Melody Sheep, and what he has done is he created this a time lapse of the universe, and it's an exponential scale starting from 2019 when the video was first published, but um, he lays it out that every 5 seconds he doubles the speed that time is accelerating, so it's exponential, and it goes through the entire future of the universe, which includes the wandering of constellations and stars. Because on our scale, again, like you said, like we won't see these constellations change very much, but once you
Mm-hmm.
fast forward thousands and thousands of years, they become unrecognizable, which is really good. So a little
Yeah,
plug for one of my favorite videos on YouTube.
that's amazing. Yeah, yeah. So it's weird to think. I mean, constellations we think of as being so fixed. They're such like a permanent part of our like our history, our lives. Like even the way that we calibrate our telescopes. Like it's like there's a glass plate in my telescope that has the constellations etched into it to align the scope.
Yeah.
But even then, there was software updates for my telescope. I think they're out every. It says to install them like every 5 years or something to account
Yeah.
for star drift because stars are moving at like dozens of kilometers a second through our
Exactly.
galaxy, right? So,
Oh,
um,
and I didn't even say the name of the video, I don't think.
oh, what is it?
So it's so the YouTube channel is Melody Sheep, but the name of the video I think is called The Arrow of Time,
Oh,
which
neat.
is really, really good video. Anyway, little short plug uh, for our sponsors out there.
Nice. Do you want to go back to
Anyway,
Orion and see what we can find there?
let's do it.
Let's do it. We'll head back to the
Let's
Orion Nebula. And so hopefully this works now, everybody. Sorry about the kerfuffle earlier. Hopefully this is not a double disappointment.
just quick check on the chat.
Okay, we are in place. Okay, don't let me down, Orion Nebula. Oh, it's already looking way better.
Here we go.
Here we go. Hooray!
Oh my God, look at that beauty. That is incredible.
All right, you wanna jump on that one? I know we chatted about this a little bit because you were carrying a blank screen for a bit, but maybe you can touch on it again.
Sure. Hold on. So, yeah. So, like I said before, like this is a stellar nebula. So, what you see there is a lot of reds and reds. So,
A lot of
not a
red,
lot
huh?
of yeah, a lot of red. But you can sort of start to see some structure as well. If you pull up like a professionally taken photo of the Orion Nebula, you see lots of curves and openings and bells. So you can kind of start to see that if you see my mouse. You can kind of start to see that with this little dark curved area here where it's almost like it's folding over on itself. And that's an indication that this is a three-dimensional structure. This little black little bowl is in front of the trapezium because it's not reflecting, or the gas is not reflecting any light back in our direction. All the reflection is happening behind the trapezium, which is why we can see reds and stuff, which is really, really cool. But kind of what else I can say, but I wouldn't be surprised that some of these little, tiny little red stars are little star babies that are just grasping at life, that kind of thing. How's that?
I think that's great. Yeah, thank you.
Capture the imagination.
Capture the imagination. So the red light in this case comes from the hydrogen gas. So when hydrogen is excited by the radiation of especially really massive stars, it will glow in red. And there's a specific red in particular that we can find with our telescopes and in our cameras. It's called hydrogen alpha, and that particular red of hydrogen light will cut through dust and gas, same with infrared radiation. So when we're trying to find star forming regions and clusters or look at them in other galaxies, they are encased, they're enshrouded in these massive clouds of dust and gas. This one happens to face us in a direction where we can see into the cavity of those stars that are forming. But if someone were on the other side of Orion and trying to look into the cluster, they would have a hard time. And so that infrared and that red light cuts through the dust and gas that we're more easily able to see. And the next generation of very large telescopes that's coming out, especially the one that's been delayed for like a long time now. But it's the James Webb Space Telescope, which is going to be the successor to space telescopes like Hubble. It will see primarily in infrared. And the reason why is so that we can see through all this interstellar glowing dust and gas to see what's inside, especially like, I think I saw a question that came up earlier from, I think, Katya, if I'm pronouncing your name correctly, but it was asking, she was asking what our galaxy looks like. And that's a good question because it's actually difficult for us to see to the other side of the galaxy because we're looking at so much dust and gas, and telescopes like James Webb will help us to map parts of our galaxy that traditionally are difficult for us to see because of all that interstellar stuff floating around.
Mm-hmm. Mm-hmm. And for all of you super science nerds out there, and even just to introduce this word to some of the beginners, is James Webb will be going to a place called a Lagrange point in Earth's vicinity. And what that means is every planet has a set of these Lagrange points. And what that means is, due to math and physics awesomeness, these are points in space where if you put a satellite there, it will not move from that position. Even if you give it a nudge in certain directions, it'll actually kind of float back to that initial Lagrange point. But this is kind of a little out there in terms of a physics and space topic. But if you're curious about Lagrange points, look it up. They are some pretty cool regions in space, in planetary dynamics, which is really, really awesome. But that's all I'm going to say about those. Intentionally.
I think SharpCap just crashed on us, so I'm gonna reboot it here.
That's not good.
It was like, this is too majestic.
Oh.
Too giant nebula. It's overwhelming.
It's too beautiful. It's like the Ark of the Covenant.
Yeah, like, don't look at it. All right, hopefully I can reconnect and everything's just fine. Seems to be. Okay, seems like everything's okay. Start live stack again. Okay, I think we're okay. Cool. So, yay, Orion Nebula showed up. Okay, should we move on?
Let's do it.
Okay, so
let's do it.
Talking about stars, we've been looking at like massive clusters of stars and forming stars and baby stars. I thought it'd be cool to look at a binary star system, so just two stars. And
heck yes.
All right. And here we go.
Slewing.
So, cool backstory on why the telescope dome wasn't open all the way. So we have this cool project that the telescope is partnering with, and it's to use our telescope to do tracked images of the International Space Station. Which is awesome. So our telescope can move fast enough to target a moving object like that. But part of it is the difficulty is the dome moves a lot more slowly than the telescope does. But because the station was passing over top, only the top part of the dome needed to be open, and then they were finished their project and then handed off to us next. But the bottom part of the dome wasn't open because they didn't need that part to be open, and I didn't double check it when I was like starting everything up. So I was like, yeah, I guess everything's good to go. So that's what happens. This is why it's important to have a
Incredible.
checklist. Even astronauts have checklists. We should have a checklist.
Oh yeah, totally.
I think we do, and I just didn't use it. That might be the case.
Yeah, really.
Now we know. All right.
Part of science. Always learn, live and learn.
Live and learn. Okay, waiting for the dome to catch up. There we go. And here we are. Okay. So all right, pull the stretch down on this a bit. There we go. Okay, so this is actually this is a binary star system called Ackyard, and I'm going to zoom in on it because this is one of those cool binary systems where you can like legit tell it's two distinct stars, which is really neat.
That is cool.
We don't have a profile loaded. Okay, hang on. Kind of resetting everything because when it crashed, we lost stuff. So let's go back. All right, here we go. Checklists do rule, Jennifer. That is true. I've gotten too complacent. Okay, here we go. So yeah, here it is. So these stars are not an optical binary or a visual binary. And that's a name that's given to two stars that look like they are close together. So similar to the example that Kyle was talking about earlier with the double cluster in Perseus. The two clusters are not actually that close to one another. They're like 1,000 light years apart. These stars are actually orbiting each other. So they are in a binary pair with one another. One is the brighter star. So this one here is a type G star. So our sun is type G as well. We are a G-class star. What's the order that they all go in now? O is the biggest. B is second biggest. K, G, K, and M. I think that's all of them. So M's are the tiniest. Is that right? I think that's right.
Yeah. No. I was gonna say an acronym that Howard Trottier would say a lot in his class is "Oh boy, an F grade kills me."
Oh boy, an F grade kills me. Oh, I like that.
Yeah.
Yeah, that's true. So anyway, so our star is G. So we're our star is not the largest of stars in the galaxy by any means, but it's also not the smallest. So we're like in the upper 25% of size of stars in the galaxy. Most of the stars are K and class M, so a lot smaller than our sun. So actually the companion star here, this one that's not as bright, this is a K-class star. So it's got about half the mass of our sun. And as a result, it's got a real sharp decline in luminosity. So it's only about 3% as bright as our sun, but it's close enough for us to see this whole system is only 20 light years away. So this is kind of in the celestial backyard of the galaxy. So this is kind of neat. So to think about how, just to give you an idea of how closely these two stars actually orbit one another, is that it's the orbit is highly eccentric. So it's meaning it's not very circular. The tiny star orbits the big one, but it's kind of more elliptical. At the high end of the ellipse, you're looking at 71 astronomical units, and 1 AU, or an astronomical unit, is the distance that that the Earth orbits the sun, which is about 150 million kilometers, more or less. But it's at its closest approach, it's only 36 AU, and by comparison, Neptune is 30. So this other star orbits kind of within the range of a solar system. So they're actually pretty close to one another, the two stars. They have an orbital period of 480 years. Now, earlier, Kyle was talking about magnitude and the brightness of the moon versus other objects in the sky. Well, to kind of give you an idea of what this would look like, this kind of alien binary star system, if you happened to be living there somewhere, if there were planets that were orbiting the larger G star, you would look up into the sky and see the K star as an object that was about 5 times brighter than the full moon in our sky. So it would be like you wouldn't have a lot of evenings. It would always be really bright. You'd have this kind of faint, this orangey reddish glow in the sky all the time, even like constantly. So it's kind of neat to think about that you'd be on another planet and see two suns in the sky. And I guess the closest to that would be Tatooine, maybe. But the thing is that because the stars orbit enough far apart from each other, you might actually have a difficulty having planets in here. We're not really sure if that dynamic is good for planets or not, because in other binary systems, the stars are close enough to each other that the planets might orbit around the common center. We call it the barycenter of mass of the two stars. It might be difficult for planets to orbit one but not the other because they might get kicked out of the solar system. So I don't know if we actually have a lot of evidence about how planetary formation happens in binary star systems like that yet. But that's, anyways, things to consider if you were living in an alien solar system of two stars.
I mean, there's a couple of planets that were actually confirmed in the Alpha Centauri system, which is the nearest star system to us, which is pretty good because that's a 3-star system.
That is a 3-star system, yeah. I think those stars are far enough apart that they can kind of exist as solar systems unto their own. But as far as when stars are close enough to each other like that I'm not as aware of. So if there's anyone any of the moderators know about evidence to that extent, it's something I need to look up as well in terms of planetary formation. When you have two bodies like that, I don't know if the gravity would actually pull apart an interstellar disk so that planets can even form or not. But yeah,
probably gravity magic. But ode to what kind of you're saying, where if you're on a planet on one of the orbiting one of the stars, the other would just be brighter than the full moon.
Yeah.
Like if you can imagine a planet being orbiting a star in one of the star clusters that we saw earlier, like there would just be no nighttime ever.
Yeah, especially like we looked at some really dense globular. There's not really any globular clusters that are up right now in the sky to see, but we have looked at some in the past, and to think that they're within a very short period of short distance from your own star system. You know, from here to Proxima Centauri, there's just us and then that other star system. Well, within 4 light years in a star cluster, you might have 100 stars or 1,000 other stars filling up your sky. So yeah, that night sky would be unreal. Well, it wouldn't be night.
Yeah. I'll just actually input one little thing as well as another binary star system. Well, supposedly binary star system is a couple called Albireo, which is actually a very popular target because of while this star system has like what looks like a very white star and kind of an orange star, Albireo, there's a very stark difference between the color of the two stars. One of them is clearly blue and the other one is like clearly red, and it's awesome. That one. Oh my god, I'm forgetting the constellation that it's in. I think it's
Cygnus the Swan.
Cygnus, I think.
Yep. In fact, Albireo means head of the swan because it is the swan's head. There you go.
There you go. There you go. You're good.
That's the one constellation trivia I know.
Yeah, really?
I'm terrible at memorizing constellations. All right.
Oh, man.
I'm going to move on.
Try and memorize all 88.
Oh, my goodness. Okay, going to move on to Messier 52. So this is another open cluster. And it's pretty close to this one, so we don't have to move very far.
Doing astronomy.
Doing astronomy.
Doing astronomy. I guess I'll use this time to check out the chatterino.
Oh, Alexander talked about Nightfall, Isaac Asimov's Nightfall. I think we've talked about that short story with globular clusters as well. Yeah, it was interesting. Do you know that one?
I haven't read it. No, I haven't read it, and I've heard so many good things about it. Oh, geez. I think I went to chapters the other day, and I think it was probably like last year or the year before. But Asimov's famous novel or short stories and novels were all reprinted again, and I picked up I, Robot.
Oh, nice.
Really, really nice. But Nightfall, I need to pick up that one as well.
So our stack, it doesn't want to stack. I'm going to turn the live stack off and restart.
Let's do it again.
It's one of those shut it off and turn it back on moments again.
Oh man, always works. Always works. So
Yeah, so Nightfall, for those of you who don't know, that short story is about a civilization that lives in a star cluster. So they don't actually ever see like the outside universe. It's too bright. And I believe, Alexander, if I'm correct, what happens is that a random freak eclipse of moon surrounding the planet that the story takes place on covers enough of the stars in the night sky that it's like they see the wider universe for like the first time, and it's like a massive paradigm shift in their society.
whoa. And that's crazy to think about too. If a civilization never knew nighttime.
Yeah, how would our like think about how much of our science is because of astronomy,
Oh, jeez.
trying to figure out what's like up in the universe.
Yeah.
Okay, here we
Holy
go.
smokes.
Trying again.
But I mean, now there's another way to collect information from the night sky, and that's gravitational waves.
Yeah,
Good
isn't that
old.
crazy? Yeah. So, do you want to tell us about that? What's gravitational waves?
Oh, geez. Okay. This is one of those kind of probably going to be a long-winded thing. Gravity waves. They are what they are is a literal distortion in the fabric of space-time. Think of if you imagine the universe as a flat fabric, um, stars, planets, objects, what they do is they make dents in that fabric. And what I'm doing is actually talking about Albert Einstein and his, because he came up with all this stuff. Like he's an incredible dude, and he came up with this analogy as well. But yeah, stars, planets, they make a dent in in this fabric, and depending on how massive they are, they'll make either a bigger dent or a smaller dent. Gravity waves, think of it as a ripple or a wave literally going out in space and time. And they are created typically when two black holes merge together to make one bigger black hole. What happens is their gravity is attracting them towards each other, and they spiral faster and faster towards each other until they merge and become one. But as they're spinning, they're emitting these gravitational waves, and we can detect those uh, here on Earth. Now they are extremely faint because they follow the inverse square law, and what that means is you can tell this thing exists where if you shine a flashlight, the farther away you walk away from the flashlight, the dimmer it gets, right? That dimming effect follows an inverse square law, and I'm sure people in the chat will definitely put up some more information. But anyway, these gravitational waves follow the inverse square law, so they are much more pronounced closer to the source than millions and billions of light years away where we are. But yeah, the ones that we do detect, they distort the fabric of space-time, but only for like the distortion is only as big as probably, I think they're saying half the width of a hydrogen atom or something like that. And it's difficult to do this on chat because I'm using my hands all the time. But if you position two lasers that are perpendicular to each other, making a right angle, and a wave goes by, what'll happen is the timing that those lasers are shot out and then reflected back to the sensor, the time that it takes for the laser to go back and forth is so precisely measured that any change in that time, no, it's not exactly the time it takes for the laser to go back and forth, but it's kind of like that. But because the gravitational waves is essentially expanding and contracting space, what's happening is the detector is getting longer and shrinking by ever so slightly. But the laser can detect that. And that's how we discover gravitational waves, is from using a facility, LIGO, that's what it's called, that that detected this, and their two lasers are perpendicular, but each arm of this facility is 2 kilometers long, essentially. So massive facility. But I'm sure people in chat will definitely expand on that. But that is what gravity waves are. And that is the other way of detecting information, because like all waves, it carries information of what happened at the source. Where electromagnetic waves or light is the primary way in a star cluster, you wouldn't be able to get any information of the outside universe. We can turn to gravity waves to detect this. And yeah, I can see in the chat that Jennifer Kirky is stepping up talking about inverse square, which is great. Awesome. But
Cool.
yeah, that's gravity waves.
That's awesome. Yeah, it's like I thought of it as like it's almost like having a whole new sense. Like before we could see the universe, and now we can also like hear the universe.
Oh my god, it's
You know?
incredible. Yeah,
Yeah.
it's awesome. So awesome.
So this is kind of we've got two more star clusters before we move off of star clusters, and we've looked at a lot of star clusters. So I'm just going to whip through this one because we're starting to run out of time. So this is an open cluster called M52, and a couple of cool things about this one is that we see a lot of what's called extinction. From the light of M52. What extinction is when light passing from a distant object is literally extinguished. It's absorbed by interstellar dust and gas. And we can tell that because if you look at, say, a cluster like this, you have stars in different regions of the cluster that are about the same age, and we know that are probably supposed to be about the same brightness, but there'll be a swath of them that seem darker for whatever reason than another, and they seem to be grouped in a similar area. And when that happens, it's like, oh, it's because those stars are being seen through a little bit more dust and gas than these stars are. And so when we notice that happening, we can actually use the light from distant stars and clusters like these to map out some of the interstellar gas between us and another object in the galaxy. And what that helps us do is kind of understand a little bit about the history or the story of where we are in the Milky Way. We talked a little bit earlier about how stars move through the Milky Way and how our night sky changes over time. Well, understanding where that interstellar gas is between us and another object can give us the history of, say, something like when we passed through the remnant of a supernova millions of years ago. We see that there are big carved out caverns in the interstellar dust and gas inside of this particular star cluster, which means a star probably blew up there a while ago. And you would say, well, how could that have happened? Because these are young star clusters. And that's true. This one's only about 160 million years old, but very large, very massive stars only live on the order of a few million years. It's like they burn the candle at both ends, and so they'll blow up really fast. Whereas a little bit more mild-mannered stars like ours can live on the order of billions of years, and then very small stars like dwarf stars, like red dwarfs, they can live for trillions of years. So it's kind of counterintuitive. The bigger stars, even though they have more fuel, burn themselves out a lot more quickly and finally explode. And so we've seen evidence of the explosion of stars within this cluster because of the shape of the bubbles of gas that exist within the cluster itself, which is pretty cool. Supernova remnants. And we've found some of those remnants on our own planet. We've actually found iron that is particular to supernova explosions. We found it on the floors of our ocean. We found it in sediment on the ocean. We find it in geological rock layers in our own planet. And so we know that the Earth is actually bombarded by particles of iron that come from supernova in the past. It's our way of tracing our story in space and time.
Forging our own story.
That's right.
I love it.
It's pretty cool.
Awesome.
All right, moving on.
Moving on.
Okay.
We got next. We got Messier 67. Let's do it. I guess.
Oh, do you want to hear? I have it moving, so
you got it.
Go nuts.
Okay, no. You can take over because I think I might crash again if I do that. Anyway, all right.
All right. Resetting everything.
Getting there.
For next target. I was wondering if you're new to us and you haven't seen this before, this is SkyX, so the software we use to point the telescope, and it also, this slit here tells us where the dome is. So we have to wait for the dome to catch up to where the telescope is pointing. Otherwise, we're literally just taking pictures of the wall, which is kind of what we were doing earlier and couldn't figure out why.
You're really. That's half our time is taking pictures of just the
wall.
inside of the dome.
Yep.
Yeah.
Yeah, so this one's neat because it's kind of a mess of different colors. Why is that, Kyle? Tell us about Messier 67.
Messier 67. I am glad you asked, co-host Matthew. Um, what we got going here? Messier 67. It is one of the oldest known open clusters. Now, again, remember when we were talking about age, where the color of the stars in the cluster is indicative of how old they are? Well, like you're going to see here, there are a lot of red stars in this cluster. So now it is open, so it's still quote unquote young, but because it has all of these red stars, it is one of the oldest. Estimated age is between about 3 to 5 billion years old. So that's pretty old for an open cluster. The total number of solar masses, or rather, how heavy this star cluster is about 1,400 solar masses. Is how big this thing is. It is 2,600 light years away, and it has about 100 G-class stars. So again, G-class is stars that are like our sun. There's about 500 stars in total, but in the next 5 billion years, because most of these stars are like the sun, so they're yellow, they're not universe-spanning ancients like red dwarfs, but they're not blue, fast, youngster blue stars. Anyway, in about 5 billion years, most of the stars in this cluster will die, either by supernova or by just planetary nebula, creating planetary nebula. And there are already 150 about white dwarf stars in the cluster. So we know some of them are already dying. So this is another clue that, most of these, or rather this cluster is one of the oldest, is because stars are already dying, which is awesome. But yeah, and like I said, there's red giants in this star. So that is one of the last phases of a star before it becomes a white dwarf, is it swells to a red giant. And the reason for that is the star has run out of hydrogen to burn, and now it's burning helium. And I'll just go on a tangent like this as well, because in the 5 minutes, promise. So if you think of atoms as like magnets, when you try and force the magnets together, like a north and a north, they want to repel each other, right? We're very tiny magnets like hydrogen. This is very easy to overcome, and it's very easy to fuse hydrogen together. The next step up is helium, which is a slightly bigger magnet. So it's a little harder to force together. So you need a lot more heat and pressure to fuse, or well, not a lot more, but you still need a little bit more of heat and pressure to fuse helium. But this star can easily overcome that criteria and start to fuse helium. Now, fusing helium produces a whole lot more energy than fusing hydrogen. So what happens is the stars will become bigger and bigger and bigger, swelling to even bigger than when it was originally, sun size. It would keep getting bigger and bigger because the more energy that it's pumping out is overcoming the gravitational collapse of its own weight. So think of it like stars are essentially just a balancing act between its own weight, the gravity, and the outward pressure of nuclear fusion. So for burning helium, there's a lot more fusion that's pushing out, so it's winning that battle against gravity. but it'll expand until it hits sort of a balance point between gravity and the own outburst of fusion. And this balancing point typically larger than what it was originally. So that is why these stars get bigger as they burn heavier and heavier elements until eventually it can't fuse anymore, and then it just collapses and explodes. Fun.
Why don't we look at one of those that might be about to do that?
Oh my God. Yes,
All
please.
right, let's do that. Yeah, so switching over now to so this Kyle was talking about stars that swell up and turn into red giants. This is actually a red supergiant, so this one's really big, and it's in part of a constellation that we've spent some time in already, looking at the Orion Nebula, but also this is the leftmost shoulder of the constellation of Orion and is known as Betelgeuse.
Oh, yes, Betelgeuse. Excellent. So, very famous one. Again, the right shoulder. Oh my God, that looks awesome. The right shoulder of Orion. And it's so big, it's so swollen that even just looking at it with the naked eye, our the cones and rods in our eyes can actually detect the color of light that's actually hitting us, which is because stars are so far away and the light has been traveling for so long, inverse square law, our eyes can't perceive color from these stars. But Betelgeuse is one of the exceptions. And let me just refer to my notes. I'm going to just rip through this object actually really quick because I see the Cigar galaxy is next, and I really want to see a galaxy. So, so again, it's the 10th brightest star in the night sky, second brightest in Orion after Rigel. And again, it's reddish and variable. So it's kind of shrinking and growing, shrinking and growing. It's unstable and it's ready to pop. And there was a scare / excitement that it was going to blow up last year, that we might have actually seen it. It's about 600 light years away, about 800 times the radius of the sun. So what this means is the size of the star is nearly out to Jupiter's orbit. So it is a tremendously large star. And when it does pop, it would be brighter than the moon. And it would be this new star, quote unquote, in the skies for weeks until it finally shrinks back down.
I heard stats on that. People said like it would be so bright that you could go out into the dark at like nighttime and it would be enough light to like read a book. But then I thought, like, is that what everyone will do? They're like, hey, Betelgeuse exploded. Let's go outside and read a book. You know, it's just like,
yeah.
I'm like, sure if that's the activity that everyone would do, like just quietly going outside under the light of a supernova to read. I mean, that would be cool. It's romantic. Maybe not at first anyway.
Oh, yeah. Just a death of a star. That really brings people together, you know? Okay. And then, it could be up to 20 solar masses. And it's, oh my God, this is great. One of the only stars we have actually properly imaged. It's one of the only stars we can actually see a sphere, a circle.
There it is. That's it.
Look at that. Look at that.
That was resolved by the Hubble Space Telescope.
Oh my God. And some of those bumps that you see, like here and here and here, it could be just like solar prominences and solar flares that are erupting off the surface. This is a tremendous object, and I love it. And while this does represent the starlight, it's also the beginning of a new one, because when this star explodes, it will enrich the surrounding area with lots of good elements like oxygen, nitrogen, carbon, all that good stuff for life. Oh! Okay, I'm excited. Let's go.
It would be kind of neat because then, like, if that it's possible that explosion could happen in the astronomical near future, like you're saying. It's like that it happen in our lifetime, but unlikely. But it could happen. And then when it does, like Orion's left shoulder will be gone. It just won't be there. Mm-hmm. Our sky will change permanently. It's amazing.
Okay, let's see a galaxy. I don't see a galaxy.
Okay, so here we go. So we did mention tonight that because of the brightness of the moon, it does wash out more like nebulosities, so there's finer, fainter objects in the sky, and that includes galaxies. But this one particular galaxy, since we were on the theme of star formation, is one that we can see. It's still kind of faint, but you can make out some of the shape of it, and it's called the Cigar galaxy, and we're looking at it edge on. So rather than the full disk of the spiralness of the galaxy, we're looking at it from the side, and so you can kind of see the edge of the galaxy. And as the telescope's moving, the reason why I wanted to bring this one up, since we were on the theme of new stars, is because this galaxy is called a starburst galaxy. So our Milky Way creates, on average, about 3 solar masses, that's the mass of our sun, worth of star material every year, between 1.5 to 3. So there's about 3, on average, 3 stars about the size of our sun that are born in the galaxy every year. So not a lot. When you think about our galaxies, enormous. It's like 150,000 light years across. It already has hundreds of billions of stars in it, but it only is making about 3 new stars every year. Well, galaxies like this one, this is the starburst galaxy, Messier 82, can be making like 30 times, or sorry, 30 up to 30 stars each year, 30 to 100 stars each year. And as it does that, it is super, super bright. So the entire brightness of this galaxy outshines our Milky Way by like a factor of 5. So it is a very, very bright galaxy. It's about 12 million light years away. Now, why does this happen? Okay, so if you go all the way back in time, about 10 billion years or so, you get to a period of history that's known as cosmic noon. And cosmic noon was a period in our past when galaxies like our Milky Way had a lot of material left in them still to be building stars. And so a lot of that material has been used up now during cosmic noon to create the stars that we now see in our own galaxy. Now, there's still hydrogen left over, and we're seeing in regions like the Orion Nebula, which we just saw, that stars are still being made, but not nearly at the rates that we used to see in history, except when galaxies interact with each other. So when they collide, or if they become very close to one another, all that leftover hydrogen that's still in the galaxy can get funneled and channeled into clumps and regions where new stars can be born. And that's when we start seeing what's called a starburst. All of these new stars being born all in one short period of time in a galaxy. So it's very hard to make out here, but this is it. This is the edge of that galaxy. And the only reason we're able to see it tonight, even under these very bright moon conditions, is because it is such a bright galaxy. Now, adjacent to M82 is a galaxy called M81, and M81 is close enough that we think that that's the galaxy that's causing the interaction of gravity between the two that's making the starburst formation happen in M82. So the reason why it's having such a rapid onset of starbirth, which is kind of neat. We see star clusters that are so big in these galaxies. So all the new ones that we've seen in our own Milky Way that we mentioned were like on the order of hundreds or maybe thousands of stars. There can be star clusters of newly forming stars in galaxies like this that have millions of stars in them. The largest star forming cluster we've seen in a coalescing galaxy or emerging galaxy is 20 million stars all forming in one place. Now, if you're around on Earth in 4.5 billion years, our galaxy is going to collide with the Andromeda galaxy. And when it does, we will ourselves go through our own period of starburst as well. The Milky Way and Andromeda together will start creating massive amounts of stars all at once. And it would actually change our entire night sky. You would look up into the night sky and see it filled with glowing regions, just like the Orion Nebula that we saw, but with the naked eye, because there'd be so much star formation going on in our evening skies. Isn't that amazing? So if you're around, then, take a photo.
So cool indeed. Yeah. Love that.
So we only got a few minutes left. Do you want to skip to the one object that we kept talking about all night that's been eating up our sky? And just go to the moon?
Yes.
All right, let's do it.
Yeah, folks, you have to be careful with looking at the moon through a telescope because that -13 magnitude can temporarily blind you. So if you're looking at the moon, definitely put some filters on, because and this has happened to me a few times where you look at it through the Trottier Observatory, and I just see this big green circle through one of my eyes for about a minute. So you got to be careful with these bright objects. So
yeah, it's amazing how bright the moon can be through a telescope. I think we have a filter, like a moon filter for the eyepiece there.
Yeah.
Yeah.
Yeah, it blocks out like 80% of the light that's coming through it, and it still hurts.
Yeah.
Ugh.
All right, here we go. Almost there.
Oh, I will say this though. We've been kicking around terms like million and billion and thousand all night. To give you perspective on how big, let's say, a million is to a billion, 1 million seconds is, I think, about 11 days. Bump that up to 1 billion seconds with a B. That cranks that up to about, I think it was 22 years. Oh my God. So a million to a billion is a massive jump in scale. So just keep that in mind when we're talking about something that's a few million light years away to something that's a few billion light years away. It's incredible. Oh, had there for a second.
Yeah, just I think the color controls are a bit off, so I'm just going to change reset the colors back to normal so it doesn't look so weird.
Yeah, we don't have a blood moon just yet.
There we go. And maybe we'll move around to something on the edge here. So I'm going to go into manual control.
Switching to manual. Whoop. That's doing some.
Getting there. All right, how's that look? Hooray, moon.
Looking good. I see a moon.
Maybe we actually go back to the Terminator because that looked a lot better.
Oh yeah, definition.
Definition.
Um,
There we go.
yeah, just looking at the chat, Louise, it's the Apollo missions. We can see, like, of course, the mares and the zones where they landed. We can see, but we actually can't see the actual landers themselves. They are very, very tiny, too tiny for our telescope to resolve. Actually, so unfortunately, we can't see the landers. But man, I can't. Eh.
Whoa, that's pretty cool.
Apollo 11 is in one of the mares. Um, anyway, it's off the screen, but we can see where they landed, but not the actual landers themselves. So kind of sad.
That is pretty cool. So Kyle, actually, you pointed out to me once, and I didn't know this before, but you can tell based on certain physical features of a crater how big it is. How does that happen?
Yeah, so I'm just kind of circling one of the craters. Um, so, okay, two things. First thing that Matthew is asking slash alluding to is that craters that have little peaks, little mountains in the very center of them, are actually craters that are more than 100 kilometers wide. And this is because the impactor, or the meteorite, that impacted the moon to create that crater, it was so big, it had so much force, because remember, force equals mass times acceleration. It had so much mass and acceleration that when it impacted, it vaporized the meteor and liquefied the surrounding rock. So much so that it behaves similar to, if you drop a drop of water into standing water, it makes a little drip effect, and this little like peak shows up in the middle, and a little ball forms. Anyway, it does that. And what it does is it makes this peak and then cools down and solidifies. But this can only happen with craters that are that large because of the mass and energy required to liquefy the rock. And then you get some of these smaller ones, and you don't see them. Um,
Oh, sorry.
Good. Okay.
Yep.
But also another indication of the age of a crater. Whoa. I'm just gonna minimize that. The age of a crater, you can tell by how sharp the crater is. like if you see these smaller ones, they're very sharp. The edges are very sharp and very defined, right? But then you get to some of these older ones, like these big ones with the very rounded edges. Um, Now, those rounding is not necessarily due to erosion, but it's usually due to, you know, like if other meteors impact the surface, the ground shakes and it disturbs the material around them, and blasts of heat and rock from impacts and all that stuff. Just over time, it does erode away the edges, but not due to atmosphere and water, like what happens with the craters on Earth. But yeah, this is just due to shaking and ejecta from other craters. It rounds the edges, but the craters with rounded edges are significantly older than craters with sharp edges. So a little couple tips there for looking at craters. Awesome.
There's actually a prominent Canadian astronomer. Her name is planetary scientist by the name of Sarah Mazuri.
Mm-hmm.
And she did a project that was really fascinating. Got a chance to talk to her about it, about the moon. And it was to date craters on the moon. Like, how do you actually know how old a crater on the moon is? And her research basically was showing, and I'm sorry, Sarah, if I've gotten this wrong, but my understanding is that what it is that you look at the edges of the crater, and
Mm-hmm.
craters that are newer, there's less wear on them, just from like space over time, not from weather, from just over time being hit by other particles of dust and just from like the sun and everything else. They will wear down so that they're not as reflective. So you can see in the
Oh,
sunlight, depending how much solar radiation or infrared energy is coming off the edges of a crater, can give you an idea of dating how old or how new the crater is. And that gives us an idea. She's using that research to narrow down a period called the late heavy bombardment in our solar system, when there was a lot of junk that was still kind of floating around. And that's the last period when there was an intense bombardment of leftover debris from the solar system's formation that struck the Earth and struck the moon. On Earth, those things have been weathered over, so we don't see the evidence of it anymore, but we can see the evidence of that still on the moon's surface because it doesn't change that often. There's no rain, no wind to change the moon's surface as much.
yeah. This is awesome.
Yeah.
And then also the new and upcoming Artemis mission
Ooh.
in 2024. This is the mission that we go back to the moon, folks. We have, hold on, with just the little bit of research that I think we did on Artemis, let me pull up my notes. Turn to the moon with the next man and the first woman to land on the moon. That is super exciting. And I think we're going to be doing lots of sciencey stuff, but this is the mission that we go back. We go back to the 2024, folks. I'm excited.
It's amazing how much resolution you get on the moon's surface out of the telescope. It's amazing.
Yeah,
Um,
really.
so there you go, Moon. We finally looked at you. You've been trying to draw our attention all night. And you are beautiful.
Finally get to see you. Yeah.
Well, I think that brings us toward the end.
Yeah. I
Maybe
think we're a bit over time,
we're even a little
actually.
bit over. So thanks. We
Mhm.
still got like the majority of you stuck around. So thank you so much for hanging out with us, everybody, and for being willing to join into our live streams, because we love doing this as much as you love watching it. So thank you very much for coming and joining in and being a part of this, because obviously we all miss being at the actual observatory and seeing you all in person. So this is the next best thing.
We miss you.
We
We
do.
miss
We
you.
miss all of our space friends, our space family.
We miss you. Oh, all of our friends, seeing everyone in person, just having a grand old time.
Having a good time. Anything else we need to cover before wrapping up, Kyle?
Uh, this has been Kyle Daly of the Trottier Observatory, joined
By Matthew
by
Simone. Hello. And goodbye.
Matthew Simone, along with our always helpful and always ready to go moderators, Indira, Abby, and from the Royal Astronomical Society, Haley and Karambir. Thank you so much, you guys. This was incredible, and we hope all you folks at home enjoyed our show.
Have a great night.
Uh,
Keep looking up.
Keep looking up. Have a good night. Never stop exploring.